If you haven't seen it yet, your exam scores are posted to Blackboard. Let's see, you already know the average was 86. I've been asked by more than one person, why did you give us such an easy test on the last one? And the answer is that I always will give the last test is going to be a little bit easier than the previous ones. It's the time of year when everything's coming at you. At the same time, I don't think it was a complete gift. I think you earned the score you got. I have received a couple emails. One person, they forgot to double the score, so it's half of what it should be. Always disconcerting when you see that the average is in the 80s and your score is less than 50. So if that happened to you, do let me know. One person had a 0, even though they took the test. That happens too, so I have found that test as well. I haven't updated the score on Blackboard yet. We will give them back, just went up to get them now. So your final exam, there is a discussion thread on Blackboard for you to post questions. So please do post some questions. Otherwise, I'll have to write them, and I don't know what kind of questions they'll be yet. I haven't decided. We're going to finish up chapter 20 and possibly 22 in the next 4 days, which shouldn't be too bad. 20 is on transition metals and 22 is on polymers. I'm going to skip nuclear chemistry. We don't need to do that one. That's boring stuff, so. What else is happening? Oh, the Chem Fiesta on Sunday. I haven't talked to the SIs yet, so I'm going to ask you guys. There's some event on the track on Sunday at like 3 or 4 o'clock. The egg thing. Our Fiesta is going on at the same time. And so the question I'm asking you is, how many of you had planned to go to the egg thing? It's an egg hunt. What's it for? Well, it's called as far as I know, it goes like this. It's the extravaganza. They put a couple thousand eggs on the football field. They have, every undergrad is invited? 14,000 eggs. Plasma TV, iPod Nano, simple little things. Yeah, it's a free-for-all. You line around the field, and when they blow the whistle or whatever, you grab as many eggs as you can. And I guess it's there should be a video on YouTube showing last year's, so you can see what it was like. Nobody has asked me to move the Fiesta, so. I will consider it, but it will be, but let me know soon. What about your papers? I can post the scores now, but they'll all be 0. You don't want me to post the scores till I'm done. I'm not going to post any scores till they're done. And believe me, every waking minute I'm still reading papers. So, what did I learn from this? It takes a long time to read 70 papers. I'm so glad I did that. Will I do it again? Yes, I will. I will just plan it a little differently. I'll assign it in the fall and collect it in the spring. You'll have your papers, but I'm shooting for this week so you can decide what to do. Somebody asked me about how to calculate your final. I know I was shooting for last week. I'm shooting for every week. When I finish, I finish. And you'll get them at that point. Somebody asked me about how to calculate their grade. It's very simple. Throw out your lowest score, whatever it is. Doesn't matter. Add up the points that remain, and that's what you've got for total points. It doesn't matter if you throw out your final exam score, an hour exam score, a paper score. Throw out your lowest score, whatever it is, and then add up the points. There's 700 possible points. If you choose not to take the final, you can take a 0 on the final. I will record a 0 score. And everyone has that option. It means that you will have only attempted 650 points. But you took a 0 for that one assessment. And so just add up the other points, whatever it adds up to is your total points. Yeah, there will be another kappa. I have one ready for you already. It's one question, and there'll be a review for the final that's kappa. No, it's out of 700. You just choose to take 0 out of a possible 150 on the final. So it works out that if you just throw out your lowest score and add up the points. No, a 90 on the final out of 150 is worth 90 points. A 90% is worth different, but that's different. And if you get a 90, then it won't be your lowest score. It's not percentages that matter, it's total points. If you choose not to take the final, you're just saying, I'll only try 650 points, but that's okay. You still have enough to get an A, right? You need 630 points to get an A. Then it gets dropped. Yes. No, you're not losing anything. If you take the final exam, okay, going into the final, let's say that you've got 628 points going into the final, and your lowest score so far is a 60. If you don't get 60 points on the final, it will be dropped. You'll still have 628 points. But you'll have got 628 out of 650 instead of 628 out of 700. If you get 62 points on the final, you now have 630 points because we'll throw out that 60 you had, and now you have a 62 to replace it. But everything's out of 700. Everything's based on 700 points. It's points. 630 up is an A, which correlates to 90%, but it's 630 points. If you have 629, that, as of the written document, is a B. Now, if you read it carefully, it says, I have the ability to lower those numbers, but I can't raise them. I guarantee you, if you get 630 points, you have an A for a grade. But I cannot raise that. I will not raise that number. I may, big capital letter M-A-Y, lower it. Don't bank on it, though. One problem isn't going to hurt you that much. So if you just didn't do one problem, don't worry, it won't hurt you that much. I will get your kappa scores to a point where you can see what they are so you can make a conformed decision. It's on the syllabus. I can't remember. I think it's 150. No. Send me emails. I've got more emails than I care to admit right now. That's the other thing I do. If I only have a half an hour of free time, I read emails and tally a spreadsheet. So, any other questions? You can sit down and figure it out, and you'll see that it works out perfectly if you just drop your lowest score. Only if you want points for it. If you haven't done it at this point, yeah, you better, because it is part of your grade. I haven't got that bonus sheet, so send me emails. I'm shooting to get that posted at the same time as I'm trying to get your extra credit posted too, folks. So, but again, that's a maximum of 10. So, you can do extra credit until the final exam. Up until the day of the final exam. So everybody go give blood the morning of the final exam. No, I don't have a bonus form. All right? Anything else, folks? All right, let's move on to Chapter 20, Transition Metals. We're interested in those compounds right in the middle of the periodic table now. First of all, anybody know what's in here? Copper. You all probably have seen a blue copper solution before. The question is, why is it blue?
Rayleigh scattering?
Not Rayleigh scattering. Rayleigh scattering is why the sky's blue, but it's not why this is blue. It's not conjugated. There's no double bonds in here, so it's not conjugated. I have to think about that one, possibly. What's unique about these elements is that the electron configurations for all of them start with 2 4s electrons and then add 3 d electrons after that. So you're adding electrons for the transition metals that have a lower principal quantum number than the 2 electrons that went in before them. And remember when we first did electron configurations, we said, okay, if we're going to pick an element like scandium, which is atomic number 21, and we figured out, okay, its electron configuration is 4s2 3d1, its outermost electrons. If you go to titanium, we keep those 2 4s electrons. And at first when we did this, that seemed a little odd. It may still seem a little odd, but the periodic table is set up to help you remember that. But because those d electrons have a smaller n quantum number, all the way across until you get to 1, 2, 3, 4 manganese or chromium. At chromium, instead of 4s2 3d4, we're going to promote one of the electrons to the d orbital. And when we put them in at the d orbital, we get a half-filled shell, and we use the argument that the d orbital being half-filled was more stable. We're not going to change that. It's still going to be that way. But now we're going to start to look at those d orbitals a little bit more. There's a nice table in your, do I want that? No, I don't want that. There's a nice table in your book that has a series of these properties. We're not going to worry about zinc because once we get to zinc, we've got all 10 d electrons filled. If you look at the electronegativity of all of those, and you think about the general trend in electronegativity. Electronegativity increases as you moved from left to right on the periodic table. Fluorine is the most electronegative element. Francium is the most electropositive. And so the trend in this first row of the transition metals holds true. As you move from left to right, electronegativity increases. There's one down step there. But remember, that's where you go to the half-filled d orbitals. And so it would make some sense that chromium might have a higher desire for electrons than would manganese because it wants that half-filled shell. And you have those 3 lumped together. And if you look on your periodic table, quite often you'll see that they are often labeled in a similar manner. On the periodic table in our book, they're labeled with a group number 8. And so, actually, iron, cobalt, and nickel they put together as 8. And so the electronegativity helps to explain it. Another trend, though, is this one. Let's see if we can do this. 147, 134. This is size. Atomic size, if you think back to what was the trend in atomic size, as we move from left to right on the periodic table, atoms get smaller because, ooh, now the because. If you're adding a proton and an electron, and it is related to the fact that you're adding both a proton and electron, except that what else changes as you move from left to right? I'm sorry? But if it's distance from the nucleus, wouldn't you expect it to get bigger as you move from left to right? More protons pull the electrons closer. The effective nuclear charge. As you move from left to right on the periodic table and take the transition metals out for a second, as you move from left to right, you're adding protons and electrons, but the electrons try to get as far apart from each other as they can, and so they look into the nucleus and they're going to see an increasingly positive charge. And so the first column sees a +1 charge, the second a +2. When you get over to aluminum, oops, the other way, aluminum +3, carbon +4, and so on. All of the transition metals, though, look into the nucleus and see exactly the same number, let's say an increasing number of electrons. As I add a proton, I also add the electron, but since they're going into an electron shell that is the outermost electron shell in their mind, if they have a mind, the size doesn't change very much. And you can see that while there is a general trend to make them smaller, if you compare it with the size of the trend that happens for regular elements, this is a very small change. So most of these, the transition metals, don't change in size significantly, at least nowhere near as much compared to the regular elements. And the reason is simply because the electrons are being added into the nucleus at a location closer to the nucleus than the outermost ones, since they're in n = 4. If I look up the reduction potentials, so I take an ion and add electrons to it to form the stable compound, what I find out is that they're all negative except copper. Copper has a positive reduction potential. What does that mean? What it means is that if I take the metal and put it into acid solution, it's going to react. Why is it going to be positive? Because what's the cell potential for hydrogen ions to make hydrogen gas? 0. And so all of these have to be reversed. They're all going to be oxidations. And so as you reverse them, you get positive cell potentials for all of them. So they should all react with acid. Okay? The question is, will they react well, strongly or weakly? So we already did that one once. We did the copper. What happens when you put copper into HCl? Actually, I think that was a test question. Put copper into HCl and put iron into HCl. One reacts, the other doesn't, and the reason is because of these reduction potentials. I'm sorry? No, these are all greater than 0 because I'm forming the ion, and those are reduction potentials I gave you. So you have to reverse the sign on all of them. Okay? So they'll all react with acid. The other thing that's interesting about these is they exhibit many oxidation states. While most of them are +2 as they're most stable, they're not all. Scandium has a +3 oxidation state that it's most stable. Titanium is +4, 5, 6, and 3, 7, 4, and 2. Iron is 3 and 2. Cobalt is 3 and 2. They'll all exhibit just about every oxidation state. Those are just the most stable ones. 1, 2, 3, 4. 1, 2, 3, 4, 5. 5 of them are +2, 4 of them +3. So as a result, their chemistry gets to be a little complex. There's lots of different things they can do. But the best thing about them is they like to form coordinate covalent bonds. They're going to bond to different things where both the electrons in the bond come from whatever's attached to it. And we've already seen this a little bit. Yeah, that's an ugly looking thing. Couple definitions, first of all. The ligand is the molecule or ion that contributes the electron pair for the coordinate covalent bond. Chelate means claw. And so a chelating agent is something that's going to grab onto it and not let it go. Some examples of some ligands that you're going to look at. Ammonia has a lone pair of electrons that can participate. And we've talked about a lot of these already. Carbon monoxide can act as a ligand with transition metal compounds. Any of the halogen ions has a pair of electrons that it can contribute. Cyanide is going to be a ligand in a lot of cases. Water, anything that's got a lone pair of electrons somewhere in it, whether it's charged or not charged, could be a ligand with these compounds. Some of them get to be a little complex. I can't spell today. Ethylene diamine is an example of a bidentate. Or a two-toothed ligand. it can bond at two places, here and here. It's often given the symbol En because no one wants to try to spell ethylene diamine all the time or write the whole chemical formula. One, two, three, four. 1, 2, 3, 4. This is the oxalate ion. The main message in all of these is that, first of all, it can be a charged particle or an uncharged compound that could act as a ligand. There has to be a lone pair of electrons. If it's going to be polydentate, in other words, it's got more than one lone pair of electrons that it can donate for a coordinate covalent bond, they have to be separated enough that I can bend around the atom. Water is not a polydentate ligand. I can't get the two sets of lone pairs of electrons to bind to two different places on the metal. Why not, everybody says. Because there's only 3 geometries for coordinate covalent bonds. They're either octahedral, they're tetrahedral, or they're square planar. These are exact same shapes we talked about when we talked about valence shell electron pair repulsion theory. So if they're octahedral, the central atom will be one of these metals, usually with a charge on it. And the charge could be any of those values up there. And it's got 6 places where it can form a ligand attachment. So if I've got a central metal atom and I attach 6 things to it, they'll be at the corners of this octahedron. In the case of copper, I can surround a copper-2 ion with 6 water molecules in this arrangement. And if I do, it'll be blue. And that's what's in that flask. So the copper has the 6 water molecules surrounding it. There has to be an anion in here too. Right now, this thing has a +2 charge. So in there might be some nitrate. And so in order to get the charge to work out, I would have to write this chemical formula as having a heck of a lot of parentheses on it. So copper, water, 6, NO3, 2. And to name this thing, you always name the cation before the anion, just like before. It's called hexa-aqua copper 2 nitrate. Hexa-aqua meaning there are 6 water molecules, there's a copper atom with a +2 charge, and there's a nitrate anion. You don't have to say how many nitrates there are because as soon as you've said the charge on the copper you know how many nitrate there have to be. A similar compound might be this. Now the copper complex ion is a copper with 6 chlorines on it. The whole ion would have a -4 charge because chlorine we know is -1. The copper is still going to be a copper 2 ion, and we need 4 ammonium ions to balance it. And so this thing would be ammonium hexachlorocopper 2. You don't have to say how many ammoniums there are, because as soon as you know the charge and everything else, it has to balance out. Some people might name it tetraammonium. The tetra is redundant. You don't have to have it in there. We're going to name a bunch of these in a second. But what I want to show you instead is I'm going to talk about these different shapes. If it's a tetrahedral arrangement, the central atom has a charge on it, and it has 4 things attached to it. And if it's square planar, the 4 attachments won't be at the corners of a tetrahedron, but they'll be in a square, a flat plane and a square shape. And what we got to try and figure out is, how the heck do the d electrons do this? So how many different d orbitals are there? There's 10 electrons in the d orbitals. Each orbital holds 2 electrons, so there's 5 different d orbitals. I showed you their picture once. Now I got to get you to look at it a little more closely. Four of them look like this. They're the easy ones. To differentiate the 4 of them, we're going to look at where they are with respect to some coordinate system. Those 3 are all going to be between 2 axes. One of them is between the x and the y axis. One is between the x and the z axis. And the other is between the y and the z axis. So in 3 dimensions, one is like this, vertical up and down. One is like this, perpendicular to it. And the third one is perpendicular to both of those. Okay? To name them, we just name their axis. So the dxy, the dyz, and the dxz are the 3 of them. And so the label tells you what axes they're between. This last one is right on the axis. And it's given the name dx squared minus y squared. And the reason why it has that name has to do with the mathematics of this thing. Anybody remember what the last one looks like? It's the one that had the P-shaped orbital with a lifesaver around the middle. It's centered on the z-axis. And it's called the dz squared. Mathematically, it's actually the 2dz squared minus x squared minus y squared, but that gets to be too much work. So those are the 5. And we've always talked about the fact that all 5 of them have the same energy. What I'm going to try and convince you now is they don't. Now they're going to have different energies. So, take this picture. Put some ligand at each position on that picture. It's got electrons in it now. And those electrons are going to interact with the electrons on that metal atom. So however many electrons there are on the metal atom, each of the ligands is going to interact with those that are there. And so now if I look at those orbitals, I say, okay, these 2 orbitals are positioned right on the same axis that those ligands are on. And there's electrons potentially in those orbitals. So now if I have electrons in this orbital, an electron in this one, and they interact with each other, they have the same charge, what's going to happen? They're going to repel each other. Does that increase or decrease the energy? It increases the energy. So those 2 orbitals, which are exactly on the axis system, are going to interact with the ligands very strongly and negatively to repel each other. Those other orbitals that are between the axes are not going to be repelled. And so where we started with 5 orbitals that had the same energy, where do I want to put it? Up there. So there's the 3D orbitals. And that's just the bare metal ion. There's no interactions with any other ligands. If I then add in a ligand, any ligand that's going to cause this thing to become octahedral in shape. So anytime there's 6 things attached to it, then it's going to arrange itself like that. Those 5 d orbitals will now split so that 3 of them will be lower in energy than the other 2. The total energy is exactly the same. We haven't changed that. So the 3 will go down in energy a certain amount. The 2 will go up in energy a certain amount. But if you averaged all this energy out, it would be exactly the same as what we had here. Now, if I have to put 6 electrons into this electron arrangement, the first 3 go just like we did before. You always fill orbitals with the same energy level first. The next electron, though, will have to choose. It's either going to pair up with this one, or it's potentially going to go up there. How do you decide which one it's going to be? Whichever one is the lower energy. If it takes more energy to pair up the electron than it does to put it into the higher energy orbital, then you would put it into the higher energy orbital. If it takes more energy to put it up there, then you would pair it up. That separation in energy is called delta. And certain ligands will have large splitting, and certain ligands will have small splitting. And where's my list? There's my list right there. And I'd have to tell you, I'm not going to ask you to memorize which ones are large and which ones are small. But what this is saying now is if I put ammonia onto a copper atom, a copper ion, ammonia has a large delta, and so it's going to split these apart quite a ways. Water, on the other hand, has a smaller delta. And so when you put the electrons into that, you're going to put those 3 and 2 orbitals closer together. What that's going to do is completely change the color of the compounds. And the reason why it changes the color is because if I take this electron and promote it up to there, I do it with light. And if I shine light on it of the right color, I can move an electron up to that higher energy state, and the different colors you get out of these compounds will tell you what that splitting is. Wednesday, what I'll do is I'll bring in something to put in this to show you that I can change, just by changing the ligand that's on here, you can change the color of the solution. All right, Jess and I are going to hand these back, so give us a second to figure out who's doing what. Alphabetically from left to right, A to Z is what it will be.